Welcome to yet another class. I'm Dr. B, your chemistry teacher. Today we are going to look at something under um, under the electrical double layer. So let us look at something under the electrical double layer. Electrical double layer. Electrical double layer. And under this electrical double layer, we are going to be looking at the Helmholtz plane. We look at the Helmholtz model. The Helmholtz model. Okay, so we are going to be looking at the Helmholtz model in the electrical double layer. Very importantly, do not forget to share. Go to my YouTube channel if you are even already there. Remember to share. Very important, please share these lectures so that your colleagues, friends will be part of what we are doing. Do not also forget to like, to comment. You can leave questions there, I will attend to them. Don't forget to also go to our Facebook page, Dr. B Science Classes or Chemistry Classes, and do not forget to share. Very importantly, share. Keep sharing. Share it to your groups, share it to your friends, comment, like, and also follow. So we are going to be talking about the Helmholtz model, and that is under the electrical double layer. Does it wonder, do you wonder at times, why is it that the milk a tin milk that you have does not coagulate? Do you wonder, why is it that the tin milk you have does not coagulate? Although ordinarily you will have had the transformation of the fats that have been dissolved in water, so to say, to form milk, to do what? To coagulate into butter. But you can hardly find milk coagulate except when the process of this electrical double layer gets destroyed. Okay, now it is because of the presence of the double layer that you have between the milk, between the fat molecules in water, where there is an expedite and constant balancing of charges between the solvated molecules in the water, which carries ions of oppositely charged, and the ions acquired by the fat molecules that go into the water. Now, in as much as there is this particular balancing of charges in terms of ions between the electrical double layer that exists just between the water molecule and the water molecule which serve as electrolytes and the molecules of the fats that are used to prepare this milk, you will never have coagulation of your milk, turning the fats into butter. Now that is the relevance of the electrical double layer. You can find electrical double layer being discussed under surface and colloid chemistry, and you will see much of it discussed under colloids. And colloids are creams, colloids are drugs, colloids are soaps, colloids are a whole lot of them, paints and all those things. Even the blood that you carry are all colloids, and you could find the electrical double layer playing a role in these things. You can also find it being taught in industrial chemistry or even chemical engineering, where you discuss parallel plate capacitors, and you also discuss the electrolytic cell, where electrodes are used in the production of certain electricity and many other things. So you can see that in electrolysis, the electric double layer is discussed, and also in colloid and surface chemistry, it is also being discussed. Now, it is a very important aspect of chemistry whenever you dabble upon them. Now, the electrical double layer was discussed by so many chemists and physicists, but there are only three models that are of very importance, of very great importance, that we used to discuss the electrical double layer, and one of those models is the Helmholtz model. The deficiency of the Helmholtz model gave rise to the Stern model. Okay, it gave rise to the Stern model. And this Stern model usually is called the diffused model. Okay, and then this deficiency also gave rise to another model that you call the Guy-Chapman model. The Guy-Chapman model. So these are the three basic models that you can use to discuss the electrical double layer. And we are going to do justice to the Helmholtz model today. In our next class, we will discuss the Stern model, and in the subsequent class, we discuss the Guy-Chapman model. And we see how the three models are different but discuss the same thing under the electrical double layer. Now, before we go ahead to talk about the Helmholtz layer, let us put down a diagram that will help us. Now, conventionally, if you have a particular part of your double layer, let's say it can possibly be a solid, can be a liquid, can be even a gaseous molecule that is being absorbed on a particular on another type of layer, which usually is a liquid. Now, if we take, for example, like we have mentioned, that fat droplets that are used in building or in making milk, homogenized milk, drop inside water. There are two different layers with two different densities and two different charges at the same time. It is conventional that once you have a particular droplet that goes into water, it will either possess positive charges or negative charges to itself. That is to say, those particular charges are usually surface charges. So these surface charges that are attracted to themselves are usually consequence upon the salt dissolution in water. Water ordinarily has the presence of negative and positive charges because of the presence of salts in them. So once you have, let's take this for example as our droplets, and we take the whole of this to be our electrolyte or water. This droplet now become your electrode at this instant, and the whole of this is your electrolyte, to mean that this droplet is in water, for example. Now, when this droplet gets into water, conventionally, depending on the strength of this particular droplet, it could at this instant and immediately carry either negative charges or positive charges from the water. So let us say that they were rather negative charges that were carried. Let's say negative charges were carried by this droplet in water. So the water itself possesses some sort of charges, okay, which are positive, negative charges, okay. So you have this kind of a situation. Okay, now when you take a look at what you have around here, you will see that basically in the solution, which is water for example, you have different type of charges that are there. And then you also have these droplets inside the water. There is a tendency that as the droplet acquires negative charges immediately, these negative charges that are acquired turn the whole of this droplet to an electrode. And it is believed that all these particular, according to Helmholtz, it's believed that all these charges that are in this particular molecule or electrode are static. So they don't move, they are rigid. Now, in order to balance these charges so that you do not have a weakness in terms of breakdown of the process of the electrodes, there is going to be a sort of solvated ions that are going to migrate, okay, and the migration of these ions from the solution to this electrode is going to be simply by a process of an electrostatic interaction. Okay, since the Helmholtz do not really believe on adsorption of molecules, do not really believe on also migration in terms of diffusion and mixing. So he believes that what will happen here, there's going to be, through electrostatic interaction, movement of what the oppositely charged ions closer to this particular molecule to balance the ions. Now, if these particular molecules move, they are going to come in here to balance these ions. They are going to come in here to balance these ions. So you now have positive ions that are drawn from the solution down to what the negative ions that are static in this electrode. In this form, you will not have a breakdown. Rather, there is a potential difference that has been created between these ions that are simply termed the solvated ions and these ions that are simply the surface ions, because these ions are the surface ions, or charges, okay, while these ones are the solvated ions or the charges. Now, these solvated ions and these surface ions will create a surface, an interface. That interface will possess a potential difference that will maintain these particular charges here. Now, because of the distance of this particular surface charges away from the solution, usually there is a gradual shifting of positive ions down to this point to maintain that double layer. Now, once the double layer is maintained, whatever you are establishing, for example, like the parallel plate capacitors, okay, where two capacitors are brought together in terms of plates, why there is a steady potential difference between both of them, it is because of what? Of the presence of the double layer. And like I had said, why blood will not also coagulate, it is in your body, it is because of what? The presence of the double layer. There is the double layer that is established. And why milk is not also going to do what? Convert itself from fats into butter, can coagulate, where that homogeneity remains, it is because of the double layer that is established. So the Helmholtz layer believes seriously in that. And he said that at this point where you have these charges, which are electrostatically being moved down to this particular surface, you describe this particular surface as the outer Helmholtz plane. Okay, and now if there is an outer Helmholtz plane, then between the solvated, the surface ions and the solvated ions, there is another plane, and this is the plane he described as the potential drop. The potential drop. And now the potential drop, okay, the potential drop is what? Is a surface or an interface, and then the outer Helmholtz plane is an interface. The two now describe what we call the double layer. And in as much as there exists a double layer, there exists a potential difference that keep that particular two surfaces, which is the electrode and the electrolyte, together. And this is exactly what happens even in your common electrolysis, where you have your electrode in the electrolyte and you have the process of electrolysis going smoothly. It is because of the double layer that is existing, because of the solvated ions and the surface ions in the electrode, okay, maintained constantly by the migration of the excess electron, which are of course the solvated ions, from the electrolyte coming down to what? To the electrode. And in as much as that migration continues, okay, there is this constant maintenance of that relationship between the electrolyte and the electrode, and there won't be a breakdown in the system. Now, apart from that, there is need for us to also understand the fact that there are deficiencies that led to what? To the Stern model. I had told us that Helmholtz, of course his name is simply known as Memon. He is Menon von Helmholtz. Now, Helmholtz himself was the very first person who discovered that whenever there is an electrolyte and there is an electrode, and an electrode is sipped in an electrolyte, there is an establishment of an electrical double layer between them due to the presence of the migration by electrostatic interaction of what solvated ions closer to the surface of what of the electrode, which of course has a static charges that does not move. And that once this these two surfaces are created, they are called the electrical double layer. And that this double layer, once maintained, will always maintain the position of whatever reaction that is taking place. Now that was done around 1850. So Helmholtz was the one who established. The problem about the Helmholtz description of double layer is that he did not take into cognizance diffusion and mixing of ions. Remember that he said these ions that are acquired by the electrode, once it comes into a solution, these ions are static and rigid. But it cannot be completely true, and that has been also proven already by Stern. Alright, it's proven because Stern believes that in as much as you still have electrostatic migration of these solvated ions closer to this electrode, there is a production of heat, thermal motion, and this thermal motion will always not allow this particular rigid electron as ions as he described to remain, but there will be a tendency of diffusion of this particular of these particular ions, surface ions, even into the solution, therefore causing some little breakup. And that is why there is a diffuse layer in the Stern model, and we're going to see later, that caution this effect. Now apart from that, he also believed that he also did not take into account the fact that there is absorption of ions. Okay, so in as much as you have these particular ions being taken by this particular electrode, there is a tendency that there could also be an absorption of ions in solution. So in as much as there is absorption of ions in solution, and there is a possibility of diffusion and mixing of ions in solution due to thermal motion, then there's going to be an effect on this rigidity he discussed. Therefore, could break this entire double layer. And that was why the Stern model came about. So when we look at the Stern model, we're going to see how these drawbacks were being adjusted. But I'm sure that you have learned something on the Helmholtz model of the electrical double layer. Now when you take some books to take a look at them, you are going to understand better from our explanation from this part or from this side of the lecture on what the Helmholtz model is all about. I'm glad that we have done this class and you have enjoyed this class as well. Do not forget to share. Very important. And don't forget to subscribe. Do not also forget to like, comment. The same thing at our Facebook channel. Don't forget to go there, Dr. B Science class or Dr. B Chemistry classes, and share, like, comment, and also follow. Until next time, it is bye for now.